So today I'm gonna continue with a new chapter. That's of course the next one called chapter 3. Our goal in this class is trying to deal forces on rigid bodies. So that's why chapter 2 stuff is not enough, because chapter 2 talk about forces acting on a single particle. But our final goal is to deal with forces acting on a collection of infinite particles, which is called the rigid bodies. So that's why, starting from this chapter, we're going to introduce some kind of new concept, which probably you already learned some of them, some part of it from your college physics. But this time, we're going to officially or systematically introduce a new concept, which is called a moment. Okay, and some of you maybe later when I introduce, you can see, oh, is that the same thing with the torque? Yes, of course, we just kind of different name, but basically we're talking about the same thing. Okay, or sometimes some books may call the generalized force. Okay, so generalized force, which is a couple, or it's called a moment, or sometimes you call it the torque. They're all talking about the same. Okay, so in this chapter, we're going to talk about rigid bodies. But in order to better understand forces acting on rigid bodies, then we need to introduce what we call a moment. Okay? And after we learn how to move forces from one point to another one, finally we end up with equivalent system of forces. The goal is the same thing. Originally in chapter 2, we're trying to see how many forces acting on one point, and then we make the equivalence, right? So we're going to have a single virtual force acting on that point, which is equivalent to those real 10 or 100 forces acting on that point. Okay? In this chapter, we're going to have a lot of forces acting on the whole rigid body. But of course, we don't want to deal with 100 forces even on the rigid body. Then what we're trying to do is whether we can find a single force acting on somewhere in the rigid body which is equivalent to those 100 forces acting on the rigid body. Okay, so this is something we're trying to do in this chapter 3 and chapter 4 later. The problem is you really cannot find that single equivalent force, which is equivalent to the 100 forces acting on different locations in the rigid body. However, if we introduce the moment concept, then we can find out two resultant forces acting on the same point, which is equivalent to those 100 forces acting on the rigid body. And those two forces, one is called an equivalent resultant force, and the other one is called the resultant moment. And that is what we want to talk about in this chapter. So finally, we still try to end up with what we call the equivalent force systems in the rigid body. Okay? So, before finally reaching that, I would like to introduce three kinds of forces in this chapter. The three kinds of moment in this chapter. The first one, we want to introduce a moment of a force about a point. That's number one, the first kind of moment. The second kind of moment we're going to talk about, or introduce, is called the moment of a force about a given axis this time. So the difference between the first one and second one is clear. One is about a point, and the second type of moment is called the moment of force about a given axis. And then we're going to further introduce the third one, which is extremely important, allowing us to move force around, which is called a moment due to a couple. And in short, this one can be also called couple or force couple. Okay, so these are the stuff we want to introduce in this chapter, and then we can naturally reach to something like this, which is called the equivalent system. So, for example, this is the rigid body, right? So normally the difference between a rigid body and the particle is basically now we are having a kind of object with some size. Because when we talk about particle, that's, you don't have the size, right? This kind of a zero distance. This 1 point. But when we talk about the rigid body, then you see the size. There's a lot of particles inside. Okay, so this time we have 100 forces acting in this rigid body at different locations. Just 1 second, please.
That's why.
Okay. So the question is, if we have 100 forces acting on different locations in this rigid body, how are we going to simplify this system? So you may say, well, I don't want to simplify it. That's fine. Then you deal with those 100 forces individually. It's not very convenient, right? So our job is to simplify, make an equivalent. Instead of having 100 forces, we want to finally end up with one force, and that's called the resultant force. at any location you choose. Okay, so you can choose this point, you can choose another point, you can choose any point you like. Once you decide you want to choose a point, then I can tell you a story to have originally all 100 forces acting in different locations, finally end up with a resultant force acting down on that point you chose. Unfortunately, if you do not have something additional, you never reach the equivalence in three-dimensional setting. So basically, in addition to this resultant force, which is equivalent, you also need to have an equivalent moment, or called equivalent couple. That's called the resultant moment. Okay, so this is the whole chapter we're trying to finally reach. But before talking about these, we need to introduce these three moment concepts. Okay, so basically, we're going to talk about the moment of a force, about a point. We're going to talk about moment of a force, about a given axis. And finally, we're going to talk about the moment due to a couple. Okay, so this is the most general kind of moment. The second kind of moment is the special case of the first one. And then the third kind of moment due to a couple, in fact, is also the special case of this, which I'm going to show you. So after we understand all these three parts, then we're going to finally solve this problem. Okay, so that is kind of the all stuff we're going to talk about in this. Okay, so ready now?
Think.
Okay, let's try.
Okay. And maybe not.
Yeah, that's I was just trying to switch. It doesn't work.
Oh, that's why. Hold on.
Oh, it's not connected?
Yeah, come out sometimes.
Oh,
There
good.
you go.
Okay, thank you. So sometimes when I see the problem, I just need to
Yeah, they can
plug again, right?
That one can come out. So just
Okay.
just double check that one.
Okay.
No big deal.
Okay, thank you.
Yeah, you're welcome.
Okay, here's my PC, right? Okay, thank you. Okay, so so I hope you have a kind of understanding about what this chapter is going to talk about, right? But before I introduce the first kind of moment, let me give you some kind of special cases, and which is also very important we're going to use. Okay, so we're going to talk about some fundamental principle in this chapter, and that is called the principle of transmissibility. If you have very special case, you don't have to learn this chapter. This chapter is more general. But if you say, okay, now I have a rigid body and I have a force acting on this point, let's say point A, it didn't indicate anywhere, just say point A, okay? So we have a force acting on point A inside the rigid body. So our job is to move this force acting on here to somewhere else. So if your goal is to want to move this force from this point to somewhere else, you have to learn this chapter first. Only under the special case, if you want to move this force to somewhere but in this force line, then you don't have to learn this chapter. In other words, this is the first concept I'm going to introduce at the very beginning. So if you want to move this force from point A to anywhere along this force line, just go ahead to move it without doing anything else. That's okay. In other words, you want to move this force from this point to this point, called point B, for example. That's fine. Just move this force, go down to here, which is called point B, with the same magnitude, with the same direction. Perfectly okay. Okay, so this one, you don't have to learn anything we call the moment. But unfortunately, it's only valid along this force line. So any point from A to here, to here, to here, that's fine. But if you want to move this force from this point to somewhere here, it doesn't work. But this principle is called principle of transmissibility. So I hope you understand whenever we talk about principle means it cannot be mathematically proved. That's called principle. Okay? When we talk about a theory or formulation, in general, we can prove that. We can show why it works. But this one normally is based on the experiment. So that's why Newton's three laws, right? So Newton's first law, second law, third law, all talking about principles. Because basically, these are the fundamental principles supported by experiment. But there's nothing you can prove that. Okay? So this is the same thing. Principle of transmissibility. So you can move a force from one point to another point without doing anything additionally. Then these 2 points has to be along this force line. Okay? That is called the principle of transmissibility. Let's just give you an example. For example, you have a truck. The engine is in the front. And then, of course, the engine will provide the drag force going to the right. Okay, so now, for whatever reason, if you want to move this driving force from this point all the way down here, that's not a problem if you want to analyze this kind of equilibrium condition problem. In other words, this is equivalent to this one. You see the difference? These three forces, self-weight and support, the same thing. But originally you have this force acting exactly at the center of the engine, for example. But now you can move this force all the way to here. The reason you can move this one to here without doing anything additionally is simply because this is in the same force line, which is called the principle of transmissibility. But in general, if you want to move this force to somewhere here or somewhere here, then you have to learn this chapter. We can still move such force to a different location, but under a condition, you need to add additional moment. And that is the moment we want to talk about. Okay? So the first kind of moment we want to talk about is the moment of a force about a point. So let's use a three-dimensional setting. Let's say this object in three-dimensional setting is a rigid body. Okay? So we have a rigid body. Now there is a force acting on this point A. This point A can be inside the rigid body, can be on the surface, doesn't matter. It's very general. Okay? So we have a point, and at this point there is a force acting at this point. Okay? So now, what's the effect of this force at this point? And that is the moment concept. In other words, what is the moment of this force about point O? Of course, the point O is any arbitrary point. I'm not talking about this point O has to be the center in the rigid body. No, you can have this point O at anywhere you like inside the rigid body. So what is the moment of this force about point O? And that's exactly the first moment, right? So the moment of a force F about a point at O. So this is the first kind of moment concept. We basically need to study such moment of a force about this point because this is going to have the effect potentially rotate this rigid body in a certain direction. Mathematically, the definition of the moment of this force about point O is this. So the distance vector cross a force vector. So before we give you the definition about this, R cross F, I need to first talk about which is called the cross product. So I'm going to spend 2 slides to talk about the cross product. So before we want to introduce the moment of a force about this point. And of course, I'm pretty sure you somehow learned cross product between 2 vectors. So I'm going to do it somehow in a quicker way. Okay? So first of all, let's say we have 2 vectors. Okay? We have a vector P and we have vector Q. So what is vector P cross vector Q? And that is called the vector product between 2 vectors. So number 1, the result is another vector. Let's say we call it vector V. Okay? So it's either called a vector product or sometimes you can see other books which is called the cross product because they use this kind of cross to indicate a product between 2 vectors. Okay? So this is the definition of vector product between 2 vectors P and Q. Number 1, because the result is a new vector, so then we need to identify the magnitude of that vector and also the direction of the vector. Okay? So that's why you see basically in order to define a vector product between P and Q, we have these regulations. Number 1, the result vector V with a cross product result V, the line of action is perpendicular to the plane containing vector P and vector Q. Because you want to do the cross product between P and Q, now you see those 2 vectors, obviously you can form a plane including or containing these 2 vectors. And then your result, which is called vector V, should be perpendicular to this plane. Okay, so that is kind of the line of action. And not only perpendicular, because perpendicular can go up or can go down. So then you need to follow the right-hand rule. For example, you want to have a P cross Q, then you need to start P first, and then using your right hand to rotate toward Q, then it should be going up. So this is the real product direction. So that's why you combine number 1, number 3, you can say the direction of the vector product V is obtained from the right-hand rule, but is perpendicular to this plane. So this is the direction, number 1. Number 2, what is the magnitude of this V? Because any vector should have a magnitude, right? So the magnitude of the V is defined as the magnitude of this P. By the way, this P is different from this P. This is the P with an arrow on top, or you can say this is the bolted, right? So this is now, that means the magnitude. The magnitude of this vector P multiply magnitude of the vector Q, and then in addition you need to multiply with sine of an angle, and this angle is the angle between two vectors P and Q. This is the definition of the magnitude with the direction, and then you can basically define a vector product. Okay, so such vector product have the following properties. Okay, number one, the result is not commutative. In other words, P cross Q is not equal to Q cross P. In fact, it's equal to negative because of the right-hand rule, right? So P cross Q is not equal to Q cross P because they are in the opposite direction. Number two, vector product is distributive. In other words, when you have a Q1 plus Q2 multiplied with P, then you can just separate out by having P cross Q1 plus P cross Q2. That's the same. However, vector product is not associative. In other words, when you have three vectors, you want to have a P cross Q and then further cross S, that is not equal to Q cross S first, and then conduct the vector product with P. That's not equal. Okay, so you need to be careful when you operate such product. Okay. The question is, how are we going to really calculate the cross product between P and Q? Are we going to use this definition? The answer is no. It's not very convenient. Okay. Instead, every time we need to calculate the components of each vector, and then we conduct the vector product. And that's a typical way to deal with a vector product. Same thing later on when we introduce a scalar product. Okay, so in other words, everything is under this Cartesian coordinate system having three unit vectors I, J, and K. So now, before we want to calculate P cross Q, what we need to do is to figure out what is I cross J. You may say, why do we need to deal with I cross J or I cross K? The reason is every vectors can be expressed in terms of ijk. And also, secondly, ijk are vectors as well. If you are talking about one vector cross product with another one, then why not talk about simple vectors making the cross product? In other words, what is I cross J, for example, right? So what is I cross J? Well, in order to figure out that finally equal to K, we need to follow the definition. The definition of vector product is number one, to figure out direction, and number two, to figure out the magnitude, right? Okay, so let's first talk about I cross J. What is the magnitude of I? Well, I is a unit vector, then the magnitude equal to 1. And what is the magnitude of J? That's also equal to 1 because it's a unit vector, right? So from this equation, the magnitude of the result equal to the magnitude of I, that's equal to 1, multiply the magnitude of J, that's equal to 1, 1 times 1 equal to 1, and then multiply sine of the angle, which is the angle between I and the J. So this is I, this is J. What's the angle between these two unit vectors? At 90 degrees. So what is the sine of 90 degrees? That's also equal to 1. So finally you end up with 1 times 1 times 1. And of course that's still equal to 1, right? So then finally you find out I cross J, the magnitude of the result equal to 1. Okay, that's a magnitude. But then we need to figure out the direction. Okay, so what's the direction? By definition, in order to obtain the direction, we need to look at number 1, number 3. Number 1 is perpendicular to that plane containing I and J. And number 2, we need to follow the right-hand rule. With these two guidance, now let's look at it. You have I this, I J here, this form a plane. So then the result must be perpendicular. That means must be in z direction. But whether it's towards the positive or to the negative of z direction depends on the right-hand rule. So when we have the right-hand rule, starting from I, go to J, you follow the right-hand rule, that's going to the positive direction of J, of Z, right? So then that's called K. So exactly that's equal to K times 1. 1 times K equal to K. So finally we can prove I cross J equal to K. This is number 1. Back to the first one. what is the cross product between two identical vectors, I cross I, for example? So what is I cross I? Well, you can still follow this one. You can still follow this one. Before we determine the direction, let's first calculate the magnitude. So I cross I, the magnitude of I equal to 1, the magnitude of I equal to 1 times 1 times sine of this angle. What is the angle between I and I with itself? So you have I this one, you have I again, and angle is 0. So what is the sine 0? Sine 0 equals 0. So 1 times 1 times 0. That finally gave you 0, right? So if you have a vector, however, the magnitude of the vector equal to 0, then you don't want to talk about. That's going to be a 0 vector. Okay? So that's why we put 0 here. So I cross I equal to 0. So following this one, any vector cross itself, that should equal 0. Then obviously j cross j equal to 0, k cross k equal to 0. All the others are similar. So let me just show you another one like this. So then what is I cross k? I cross k, the magnitude equal to the magnitude of I, that's 1, times the magnitude of k equal to 1, 1 times 1, and times sine of the angle between I and k, that's still 90 degrees. Sine 90 equal to 1. So 1 times 1 times 1, that's equal to 1. So the magnitude is also equal to 1. Then we look at the direction. So the direction follows, number 1, perpendicular to I and k. And second, follow the right-hand rule. Let's go back to look at this one. This is I and this is the k. And the result should be perpendicular. That means in y direction. Now you need to use a right-hand rule to follow and to see whether from here to here, that's going to be going down. So then the result, the direction is going to the negative direction of y-axis, which is called the negative j. So negative j showing the direction, and then times 1. And you don't have to write 1 times this. 1 times anything equal to that self, right? So basically, I cross k equal to negative j. So if you can follow this one, then basically you can get these. These are important equations for us to deal with any cross product between two vectors. Now let me just quickly show you how to deal with vector p cross vector q. P can be split into 3 components, px, py, pz, ijk, cross 3 components of vector q, qx, qy, qz. And then you just basically follow what we had, the distributive rule, so that you just do 1 by 1. So this one cross this, I cross I equal to 0. Then you need to forget about this term. And then this one cross this one, I cross j equal to k. Then it's going to be px times qy, px times qy, multiplied by k. So that's the one term. And so on. Originally, 1, 2, 3, 1, 2, 3. Basically, you have 9 terms, right? You're supposed to have 9 terms. But 3 of them are 0. So you only have a 6 term left. So those 6 terms with anything in front of I, you put them together. Anything in front of j, you put them together. Anything in front of k, you put them together. That's the result. So in other words, this is the equation allowing us to calculate the cross product. So in other words, this is a definition of the cross product. But we're not going to use that because that's too time consuming, too much time consuming. Instead, this is a basic way we are trying to calculate a cross product between P and Q. Find out 3 components of P, find out 3 components of Q, and then make this product. If you still do not know how to deal with cross product, at least you need to memorize this. Okay, but I normally do not memorize this. Every time I just got 3 components, I just do 1 by 1 because I know these very easily. There's another equation to show you the result, which is, in fact, this result is the determinant of a 3 by 3 matrix. So if you are pretty familiar with the matrix, you are pretty familiar with the determinant, then that's also fine. You can use this equation. So this equation shows you need to write the first row, which is always ijk. The first row in that for that 3 by 3 matrix is always ijk. And then you need to determine the second row. So the second row are the 3 components of the first vector, vector p. 3 components. And then the third row are the 3 components of your second vector q. And then you basically identify those numbers, and then you need to calculate the determinant of this 3 by 3 matrix. So your final result should not leave like this. This is not complete result yet. So if you are doing this one, you don't want to memorize this one, or you don't want to deal with the cross product term by term, then you need to know how to deal with or how to calculate the determinant of 3 by 3 matrix. It's really up to you. Okay? So this is the definition of vector product. Originally, we have the definition here, but in reality, this is the real equation normally we use to make the product with explicit terms.